All right, we are going to start with derivatives of exponential and logarithmic functions. So you need to go to the page in your notes that has the derivatives of transcendental functions. And the first part of these notes is just going to be, well, actually all of this is going to be filling in those. So I don't want you to do the example problems. I would just kind of try those on a separate piece of paper, but don't put them in your notes unless you have space. We do need to do the natural logs and exponentials, and then the next section will be inverse trig functions. So again, it would be nice if all of these were on one page in your notes like we talked about. So again, I wouldn't put those examples in if you can refrain from doing so. So our derivatives of exponential functions, I'm just going to start by kind of discovering the derivative of the natural log of x, and then from there, and again, you don't need to write this in your notes, just enjoy the show. And then the other ones I'm just going to give you. These derivatives of transcendental functions need to be memorized. There really aren't a ton of things in calc that I'm going to say you need to memorize. The reason I wanted all of these rules on one page is so that you had one easy reference when you're studying as the test approaches to kind of reference. And we'll make some Quizlet lives and all that kind of stuff too, but it's nice to just have them all in one spot. So let's just discover the derivative of the natural log of x. So our goal here is to figure out what d dx of the natural log of x is. And what we're going to do is we're going to say, let's let y equal the natural log of x. And we don't know what this derivative is yet, but we can rewrite this in a different way. So I'm going to rewrite this as e to the y power equals x. And now I'm going to take the derivatives of both sides. And since now we've done implicit differentiation and we've done the chain rule, we can do this. So we know if we're taking the derivative of e to the y with respect to x, it's going to be the derivative of e to the y multiplied by dy dx. And that's going to equal the derivative of x with respect to x, which is just 1. Now, just like we did in class, we're going to go ahead and get dy dx by itself. So I now have dy dx equal to 1 over e to the y. All right. Well, I know from up here, this is similar to that circle problem that we saw, I know that e to the y equals x. So I know the derivative of my original function y with respect to x is just going to be 1 over x, which is pretty cool. So in your notes, what I want you to do is write out under the natural log and exponentials, d dx of the natural log of x is going to equal 1 over x. Keep in mind that if this is something other than x, like if this is a u, if we have the derivative with of d dx of the natural log of u, that would be 1 over u, so 1 over whatever's in here, multiplied by u prime. So the chain rule still applies to all of these situations. So you just need to kind of keep that in the back of your head, that the chain rule doesn't just like completely disappear because this is a new rule for a certain function. The chain rule still applies. And we'll see that in some of our examples. We also have the derivative with respect to x of log base a of x. And that's going to equal 1 over x multiplied by the natural log of a. And a has to be positive, so that's totally fine. And then lastly, we have d dx of a to the x. And that's going to equal a to the x multiplied by the natural log of a. And again, the chain rule still applies in all of these situations. So if we had something other than x as our exponent, we would then have to multiply that whole expression, a to the x times natural log of a, by whatever the derivative of that exponent would be. So let's see these in practice. Oh, sorry. Let's go back. There we go. And again, just kind of pay attention. You don't need to actually write these down unless you have a space that's not in your notes, not in this page to write those down. So let's say we want to find the derivative with respect to x of log, we'll say base 2 of x plus 5. So if this is our problem, we're going to look at our rules, and our rules say that we have a log base a, which is our situation, of some expression that's going to be 1 over whatever that expression is times the natural log of whatever this base is. So we're going to start off by saying, all right, we have 1 divided by this expression, x plus 5, multiplied by the natural log of 2. And in this situation, we do technically need to multiply by the derivative of this function, but the derivative of this function is just 1, so it ends up just being 1 over x plus 5 times the natural log of 2. Let's try another one. Let's do d dx of the natural log of sine of x. So obviously there's some domain restrictions in this situation because natural log can't be less than 0. So there are some values that we wouldn't actually be able to input to x due to natural log's domain restrictions. But just looking at this in its expression form, our derivative of the natural log of anything is 1 over whatever that is, multiplied by the derivative of this inside function. So we're going to have 1 divided by sine of x multiplied by the derivative of sine of x, which would be cosine of x. So we would end up with cosine of x over sine of x, which would yield cotangent of x. Let's try one more. Let's say we're doing the derivative of 5 to the 3x squared power. This rule tells us that it's going to be this expression, so 5 to the 3x squared multiplied by the natural log of 5, so that a term. Notice that's a common theme between both logs with a base that's not the natural log, as well as exponentials that don't have a base e. And then we need to multiply this because of the chain rule by the derivative of this exponent, so 6x. So we would end up, I'd probably write this as 6x times 5, 3x squared, multiplied by the natural log of 5. It really doesn't matter what order you write this in, as long as you don't think that one of these expressions is within your natural log. So parentheses would obviously help you out there. All right, you're going to hopefully try these on your own somewhere on a separate piece of paper on a whiteboard, and now I'm just going to kind of go through those solutions. So for this one, we would have f prime of x equal to, we're going to do 2, we're going to have 1 over whatever this inside function is, which is x, multiplied by the natural log of 2. So notice all of my logs are 1 over some expression. And then from here, we would just subtract the cosine of x. If we have just 5 to the x, f prime of x is going to be 5 to the x times the natural log of 5. For this next one, we have g prime of x equal to, and now it's going to be 1 over whatever's on the inside, which is 2x cubed, and then we're going to multiply by the derivative on the inside, which would be 6x squared. These logarithmic functions can oftentimes be simplified quite a bit. So this would end up just being 3 over x. And then for h prime, we're actually going to look at this in 2 different ways. If we just follow the rules, the natural log would be 1 over 5 to the x. Then we need to multiply this by the derivative of 5 to the x, which would require using our a to the x rule, which would say we need to multiply this by 5 to the x times the natural log of 5. Well, notice my 5 to the x's would cancel out. I would just be left with the natural log of 5. Another way that we could look at this and get the exact same result out is if we rewrite h of x, remember our log rule said that if I have the natural log or the log of something to a power, I can bump that x term to the front. And so these two expressions are mathematically equivalent. As a result, if I were to take the derivative of this, ln 5, although it doesn't feel like it, ln 5 is a constant. So h prime of x would just be the natural log of 5 because we're just taking the derivative of some constant times x. That same thing applies over here, which is why we get the answer we get. We can rewrite g of x in a couple of different ways, but one way would be 3 times the natural log of 2x. But then remember, when we have multiplication on the inside, it equates to addition between logs. So that's the same as 3 times the natural log of 2 plus the natural log of x, or 3 natural log of 2 plus 3 natural log of x. And if I were taking the derivative of this form of the equation, I would get g prime of x equal to, well, this would be 0 because there's no x term, so that would just go away. And then we have a coefficient of 3 times the derivative of the natural log of x is 1 over x, so we get 3 over x that way too. So sometimes with our logs, it is actually going to be a little bit easier to break these down using our log properties. And if we had the time to, we could also go through why this rule for log base a of x gives us out the solution with a natural log of 2. I'm not going to go through the whole thing, but if you're interested, I believe it's in the textbook in this section, but it does deal with a change of base formula and just then going through a quotient that way. So just a heads up on that front. All right, the next thing that we need to take notes on are derivatives of inverse functions or inverse trig functions. Next week, I'm going to go through taking the derivative of an inverse function. You don't need that knowledge for these trig functions because we really are just going to memorize. And you know I'm not a fan of memorizing, but there are just a few things we do need to have memorized. So the first thing we just need to clarify is that on the AP exam, you're actually going to have this written at the beginning of every AP exam. It's going to just specify that anytime you have an inverse, so f to the -1, which is how we saw it last year, we're using trig functions, you can see it written in two different ways. So you can see it written as the inverse sign using sine to the -1, or in other texts and in other resources, you may see arc sine of x. These are equivalent. They're just two ways of writing the exact same thing, and the AP test really bounces between the two. So you could see arc sine of x, and you need to identify that as inverse sine of x, or you may see sine to the -1 of x, and you need to identify that as inverse sine of x. So just make sure we're familiar with both of those, and both will pop up throughout. All right, so here's how and I actually just learned this, here's how we're going to memorize these inverse trig functions. So notice that, so first of all, they're all going to be fractions. So I'm going to go ahead and change this color so you can really see it. I'm going to go ahead and put a fraction bar in each instance because all of these are going to be fractions. And then I'm going to start with sine and secant. And notice that both sine and secant are the only two trig functions that start with the letter S. And so we're going to remember that they're going to involve a square root in the denominator. This one I'm going to leave a little bit of a space, so leave a little bit of space and then draw your square root. And they're also going to involve subtraction. The next thing I notice is that sine has an I. And I looks a lot like the number 1. So for sine, we're going to write 1 subtract x squared. And for secant, we are going to write x squared subtract 1. So notice the term that has the I, the 1 comes first. The term that doesn't have the I, the 1 comes second. So they're the reverse of each other. This is x squared, subtract 1. Sorry, it's so messy. Then they're each going to have a 1 in the numerator. The only thing that's different about this one is that it also needs to have an absolute value of x in front. The reason I had you do these two first is because, again, the s means square root and subtract. And then because this sign has an I, we went ahead and wrote the 1 first and then subtract x squared. They're all going to have that x squared term. On this one, the I was not there, so we wrote x squared first. All right, so cosine is going to be the exact same thing as sine. The only difference is that it's going to be negative. So it's going to be a negative 1 over the square root of 1 subtract x squared. And secant and cosecant are going to follow the same logic. So negative 1 over the absolute value of x, the square root of x squared, subtract 1. So notice if you know sine and secant, and you can remember that with subtraction and square root, and then you have the I to remember 1 minus x squared, then you know what cosine is. And if you know secant, you know what cosecant is. Lastly, we have tangent and cotangent, which are going to follow the similar logic of having a 1 and a negative 1. So notice all of these are positive and all of these are negative. All of the C's are negative. And then tangent, T kind of looks like a plus sign, right? Well, with tangent, we're going to have addition. So we have 1 plus x squared, or you could write that as x squared plus 1. It doesn't matter. And we have the same thing over here. And remember, addition is commutative, and so it doesn't matter what order you add those in. So just to kind of recap, that S means square root and subtract, and that occurs for both of these. And you just have to kind of remember that absolute value in there. And then for tangent, T kind of looks like a plus sign, or you have this A, which means addition. And so you have 1 plus x squared. But other than that, they're all pretty similar functions. So what we're going to do now is just look at the application of these in simplifying some problems. So here we're taking the derivative of arc sine of 3x, or inverse sine of 3x. So when we do this, because this isn't just an x, we need to use our chain rule. So what we have as our rule is 1 over the square root of 1 subtract x squared. So what this is going to look like, since we have a 3x here, is 1 over the square root of 1 subtract 3x all squared multiplied by the derivative of this inside, which is 3. So we end with 3 over the square root of 1 subtract 9x squared. Oftentimes, these types of problems show up in the multiple choice. I haven't really seen any examples of these inverse trig functions showing up in the open-ended and then you needing to apply that, just because they know this is a more challenging area. And it does require memorization. They really want to know that you know the math, not that you're capable of memorizing certain things. So let's follow with tangent. Tangent is the one that's going to show up the most frequently. Tangent and sine I've seen the most frequent, but you never know. They could throw in anything that's in our course description. So again, we have 1 over 1 plus whatever this inside is squared, so 2x squared all squared, multiplied by the derivative of the inside, which would be 4x. So we end up with 4x over 1 plus 4x to the 4th. Last but not least, we have arc secant. So for arc secant, we know that this follows 1 over, we have the absolute value of x times the square root. This is a subtraction, 1 subtract, and it doesn't have the I, so let me rephrase that. That's going to be x squared subtract 1. All right, so we have 1 divided by the absolute value of 5x multiplied by the square root of 5x all squared, subtract 1, multiplied by the derivative of the inside, which is 5. So we have 5 over the absolute value of 5x times the square root of 25x squared, subtract 1. Now let's just simplify. We're going to look at some examples without actually having to do the derivative of how to simplify these. But we just want to think about, you can simplify an expression outside of absolute value, an expression inside of absolute value, provided you know that that value is going to be positive regardless. So we know that 5 is positive regardless of being inside my absolute value or outside my absolute value. So for that reason, I can rewrite this as 5 times the absolute value of x. As a result, I can cancel out these two 5s, and I'm left with 1 over the absolute value of x times the square root of 25x squared, subtract 1. Let's just look at these expressions to see how they would simplify. Here, the 3 I know I can take out. So I have 9x squared in my numerator. This denominator I'm going to rewrite as 3. And then I have an x cubed here. Well, if I sub in a negative 1, that's not that, and then I take the absolute value, that's going to change my answer from negative to positive, right? But what I can take out of there is an x squared. So I'm going to, because if I put a negative 1 into x squared, I get a positive 1, right? So it's like I'm rewriting this as 3x squared times x. And I'm saying, well, this expression has to be positive. So I'm going to take that out of my absolute value and just leave in that absolute value of x. I'm still ultimately multiplying these out, right? It's just forcing that final x to be positive. So I can rewrite this now as 3x squared times the absolute value of x times the square root of 9x to the 6 subtract 1. And now I can simplify things a little bit. That can cancel, and those can cancel. So I'm left with 3 over the absolute value of x times the square root of 9x to the 6 subtract 1. The same can apply over here, but in this case, notice I have an x squared, so if I put a negative in here, it's still going to be positive, and I'm taking the absolute value of a positive. So I can rewrite this as 4x over 2x squared. I can get rid of the absolute value times the square root of 4x squared, subtract 1. These are going to cancel. This can cancel with this. So I can go ahead now and I can cancel my 4 and 2 cancel to just be a 2, and then I can cancel this x out and drop this down to a 1. And so what I'm left with here is 2 over x times the square root of 4x squared subtract 1. And the reason I was able to do this is we can go ahead and substitute in a negative 1. So let's say I put in a negative 1 into this expression. I'd have a negative 1 and a negative 1. That would give me negative 4. If I put a negative 1 in here, right, that's going to force it to be positive over 2 multiplied by what? 4 minus 1, square root of 3. Well, if I put a negative 1 in here, I get 2 over negative 1 times the square root of 3. So I still end up with the exact same output because I still have that odd degree overall for my variables there that force that negative result if I put a negative in. Obviously, if I put a positive in, I'm going to get the same result back out. All right, so this would be my end result here for simplifications. The only other thing we want to talk about is when you're evaluating these inverse trig functions, remember from last year, they have restricted domains that we have to worry about. So remember we can only go from negative pi over 2 to pi over 2. So we replace that with a 3 pi over 2 cosine, we said was this half circle, and then tangent was negative pi over 2 to pi over 2. So sine and tangent maintained the same. Cosine, inverse cosine was from 0 to pi. Just to kind of back this up, inverse cotangent was also this domain of 0 to pi. Cosecant, inverse cosecant was negative pi over 2 to pi over 2. And inverse secant was also negative pi over 2 to pi over 2. All right, so let's just evaluate, and then I think I just have a problem for you, and we'll be good to go. So let's say we have f of x equals arc sine of x, and we want to evaluate that at x equals 3. So we're going to go ahead and take the derivative. Oh, no, we're just doing this out. So f of root 3 over 2. We want to know what the inverse sine of root 3 over 2 is. So if you think about this on your unit circle, we're talking about our y value being root 3 over 2. So that's our taller triangle. That's pi over 3. So our answer would be pi over 3. If we were looking for a negative root 3 over 2, our answer would be negative pi over 3. So it all depends on what we're looking for. But remember, we have to stay between these two quadrants. And we're using those negative angles rather than using the traditional angles on the unit circle for those. All right, here is your practice problem. Let's give it a go. Hopefully you did well. So we're given the function y equals inverse sine of 5x, and we're evaluating the derivative when x equals negative root 3 over 10. And we want to write the equation of the tangent line at this value. So the first thing I'm going to do is just write out my ordered pair. I have negative root 3 over 10. And I'm going to go ahead and sub in for my original function this value to figure out what my output is. And this is straight from that other problem. We have inverse sine of negative root 3 over 2, which is going to be a negative pi over 3. So I know that this is my ordered pair. So now I'm going to go ahead and take the derivative of this function. So I'm dealing with arc sine. So remember subtraction and square root. I have 1 over the square root of, I have that I in there, so the 1's going to go first. Subtract 5x all squared times the derivative of this inside function, which is 5. So I end up with 5 over the square root of 1 subtract 25x squared. And now I want to evaluate this when x equals a negative root 3 over 10. That's going to equal 5 over the square root of 1 subtract 25 times negative root 3 over 10 all squared. So we get 5 over the square root of 1 subtract 25 multiplied by 3 over 100. We have a 1, we have a 4, so we have 1 subtract 3/4, which is just 5 over the square root of 1/4. Well, the square root of 1/4 is 1/2, so I have 5 divided by 1/2, which is the same as 10. So the equation of my tangent line would be y, I'm over here, so plus pi over 3 equals 10 multiplied by x subtract a negative root 3 over 10. That's all, folks.